Great. Okay. Thanks, everyone, for joining us for this colloquium. It's my great privilege and really honor to introduce today's speaker, Professor Margaret Murnane from the University of Colorado at Boulder. She's a fellow of JILA, the Joint Institute for Laboratory Astrophysics, and director of STROBE, a new institute that she founded to push the next frontier in microscopes and light sources. In the way of background, Margaret received her BS and MS degrees from the University of College Cork, so she's Irish, and a PhD from physics at the University of California, Berkeley in 1989. She joined the faculty at Washington State University in 1990 and immediately made a hit with the whole world, at least the chemistry community, in developing ultrafast lasers that were made possible, were basically distributed to everyone. It was a very generous offer, and everybody knows Margaret in the field, let me just say that. In 1999, Margaret moved with her husband, Henry Captain, to the University of Michigan, and so in 1996, and then 1999, she moved to UC Colorado. Margaret's research is in ultrafast optics and X-ray science. She has a long list of honors and awards. I think in the short bio that you saw, the one most outstanding one could say is the 2021 Benjamin Franklin Medal in Physics. This is shared, this has been shared by, this goes a long way back in the Franklin Institute. It's been shared by people's notorieties such as Marie Curtis, Thomas Edison, Albert Einstein, Hawking, Jane Goodall, and apparently Bill Gates. She's received the Presidential Distinguished Service Award from the Irish abroad, the Willis Lamb Award for Laser Science and Quantum Optics, the Boyle Medal, the OSA Wood Prize, in 2010, the Arthur L. Shallow Prize in Laser Science from the APS, 2009, the Ahmed Zewell Award. She's a member of the National Academy. She's a fellow of the American Association of Advancement in Science. And in 2000, the one award that I remember the best, at least my own personal opinion, was in 2000, she was awarded the MacArthur Fellowship. And I should also note that she won in 1997, was awarded the Marie Goldberg Meyer from the Award of the American Physical Society. So she's has a lot of awards and recognition. It's just a statement that she's been doing pioneering research and really inspired a lot of people. And she's one of the absolute best mentors. I've had one of her students over a summer visit and was really impressed with the training that she received under Margaret's tutelage. So without further ado, I will give you Margaret to present her colloquium entitled Attosecond Quantum Technologies for Probing the Functional Properties of Materials. Margaret.
Thank you so much, Dwayne. Can you hear me okay?
Yes.
Awesome, awesome. So Dwayne and Paul, I so much appreciate the opportunity to visit. We're sad it's remote, but looking forward to a better 2022. And Dwayne, thank you for the introduction. And of course, the way we all do science, and I know yourself also, is through just a very large group of current group members, alumni, collaborators, and folks who really want to take these ultrafast lasers and X-ray sources and make them more robust for applications. And so I also have to thank the team at KM Labs, and I'll mention people's name as I talk about the work. And so as Dwayne said, this afternoon, I'd like to talk about how we use attosecond quantum technologies and apply them in material science to learn about new properties of materials. And I'd like to touch on 3 topics today. So the first topic is just a very brief introduction to where we are in terms of this high harmonic generation light science. And I joke with my laser scientist friends that through quantum mechanics, we now have better control over X-ray light than we have over visible light. And that's just when I'm trying to get them to have a good animated discussion with them. But there is a good argument that can be made in that way. So I'll tell you about high harmonic generation, and then tell you a little bit about a few applications in material science that are quite surprising. In any material we've looked at, we've learned something new about the material. And then because of the time scale it takes to take a new technology and use it for real world applications, I'd like to spend just 5 minutes talking about the use of high harmonics in industrial research and development. IMEC is now using these sources to answer fundamental questions in materials that are needed to develop the next generation semiconductor and quantum material systems. This took a long time. This light source I'm going to talk about was first observed in 87 and 88, and it's really only in the past few years that people are adopting it seriously to develop new types of materials and to understand existing materials. Okay, so the high harmonic generation is a tabletop source of coherent X-rays. And of course, X-rays by themselves, even incoherent sources of X-rays, are extremely powerful tools. They can penetrate visibly opaque samples, and they have inherent contrast. So if you have an X-ray beam, you can tell what element one is looking at by the position of the absorption edges. And also the chemical state or the magnetic state is also encoded in these positions. Under many conditions, one can implement non-destructive imaging. And if one has coherence, one can focus the X-ray beam to the wavelength limit, and also make these incredibly short pulses, shorter than almost any process that's relevant to a functional system. But for these last 2 points, that we do need coherence. And for a long time, we did not have that in the X-ray region. In the visible, we've had just beautiful coherent laser sources now for over 60 years. And for those of you who are not expert, it might be surprising to hear that the first laser was demonstrated back in 1960 by Ted Mayman. And he built a ruby laser that lased in the red just below 700 nanometers. And in that intervening 60 years, the shortest wavelength laser that's in widespread use is the excimer laser at a wavelength just under 200 nanometers. And excimer lasers are in widespread use to print all the chips that make up our cell phones and computers and Internet of Things. And one reason that it's progress in shortening the wavelength of lasers is that it requires a great deal of power to make a population inversion and make a laser that works at shorter wavelengths. And high harmonic generation circumvents that. And so it's one of the few sources we have that can make a tabletop tunable wavelength laser-like beam that can span from the ultraviolet to under 10 nanometers. And so that makes it very interesting. So what do we do for high harmonic generation? What we do is we take femtosecond lasers where they're relatively straightforward to implement these days in the ultraviolet or near infrared or mid-infrared region of the spectrum, and focus them in our group, we use gas-filled waveguides. And then if we tailor the color of the femtosecond drive laser, then we can generate short wavelength beams that span from the vacuum ultraviolet to the extreme ultraviolet to the soft X-ray region. Now, the way I've explained this, it's sort of thinking about harmonic generation as a nonlinear optical upconversion process. So it's a little bit different from that, and we can see that by looking at what's going on in an individual atom when we focus a femtosecond laser pulse onto, say, atoms in a gas jet. And if you just look at this top figure here for now, So under the action of this intense laser field, you don't need much energy, but if your pulse duration is short, the field is higher than the field that binds the electron to an atom. So the atom can ionize, the laser field is stronger than the Coulomb field, and so that drives the electron away from the parent ion. And when the laser field reverses, the electron can return, recombine, and liberate its energy as an X-ray. So in that cartoon on the top, you could think about harmonic generation as a sort of a Bremsstrahlung-like radiation, but the quantum picture is shown here in this movie at the bottom, where essentially one starts with this is a 2D representation of an electron, let's say in the ground state of hydrogen. When the laser field irradiates the atom, it drives tunnel ionization, and that sculpts this very beautiful spatially modulated electron wave function, and a corresponding very rapidly changing dipole moment. And so that's why, although we're driving the electron wave function at the fundamental frequency of the femtosecond laser driver, the rapidly changing wave function in time gives us a dipole moment that has very high order frequencies. And this is the origin of the high harmonics that allow us to take, let's say, a mid-infrared femtosecond laser and upconvert it into the extreme UV and soft X-ray region. So this was all discovered by beautiful work back in the late 80s and early 90s. And just from a 40,000 foot view, then one question in our group that we had is, so how do we engineer this beautiful quantum physics and make a useful light source? And so for that, we need to do two different things. We need to know how to sculpt the dipole that I just talked about. And the beautiful thing is that allows us to map the phase of the laser onto the phase of the electron wave function, which in turn maps onto the phase of the radiated X-ray fields. And the other thing we have to do is we have to manage dispersion so that we can add the X-ray emission from millions and billions of atoms. And the reason for that is that each atom is emitting in a dipole distribution. So there's no directed beam from any one atom. But if we can arrange that both the laser and the X-ray fields are propagating in phase through the medium, then the ionization, recollision, and emission of those X-rays will add coherently, and so we get a directed beam. Since we have to add these waves to a fraction of their wavelength, it turns out we need this process to be to have a precision of sub-attosecond in time and sub-angstrom in space, which is quite challenging, but nature does it passively. And we are very fortunate it does, because we don't have modulators that could work with anywhere near this precision. So this is the only one of the few equations I show in the colloquium today, but it's at the heart of how we make phase matching work. So what we rely on is the fact that when a femtosecond laser pulse travels through a medium, it starts to ionize the medium. Now, on the leading edge of the laser pulse, the laser is traveling in a neutral gas, and we all know that when light travels through glass or gas, its phase velocity slows down to less than the speed of light in vacuum. But the X-rays because their photon energy is well above all the resonances in an atom, they are traveling at the phase velocity given by the speed of light in vacuum all of the time. So on the leading edge of the laser pulse, the phase velocity of the laser is less than c, and that means it's less than the phase velocity of the X-rays, so they are asynchronized. So we don't get good coherent addition. On the trailing edge of the laser pulse, we have a similar situation, except now the laser is traveling in a plasma, and the phase velocity of the laser in a plasma is greater than the speed of light in vacuum. But we are very fortunate that for every laser color we have investigated, there is always a window during which the part of the laser pulse is traveling at the speed of light in vacuum, exactly synchronized to the X-rays. So we call that the phase matching window. It changes if we change the laser color, but it's present for every laser driver we've looked at. And it has a very large effect on the type of emission we see. Because if you can imagine, if you have multiple bursts that are phase matched in time, that will correspond to a picket fence in frequency. If you have a single burst that's phase matched in time, that will be a coherent supercontinuum. And you can see that imparted on the type of spectra we generated. So for example, if we drive high harmonic generation with UV lasers, we can phase match multiple bursts. So you get a very narrow picket fence of a comb of harmonics. But if we drive high harmonic generation with mid-infrared lasers from 1.5 and 2 and 3 microns, then only 1/2 cycle of the laser is traveling at the speed of light in vacuum. And so we get a true coherent supercontinuum. And then in between, we get combs with a broader individual width because fewer cycles are phase matched. And the type of flux we get in terms of photons per second are very nice, because in all these regions, we have plenty for application experiments that I'll talk about in the next part of my talk. So just summarizing this first part of the talk, we have a recipe now and this is just the simplest way of implementing high harmonic generation, where if we want to make bright UV and vacuum UV light, we drive with UV lasers. If we want to make light, say at 13 nanometers, we drive with Ti sapphire lasers. And if we want to make a soft X-ray light, we drive with mid-infrared driving lasers. And the characteristics in time and the spectral and temporal characteristics change, but we know how to predict those and control them in a very nice way. And one of the ways that we and several other groups have been exploring recently is tailoring the spin and orbital angular momentum of X-ray beams. That has long been done, of course, in the visible region of the spectrum, to probe magnetism and chiral molecules, and then more recently, of course, for super resolution imaging, generating vortex beams. And it turns out that these same tailoring can be implemented in the X-ray region, but in the X-ray region, it is much harder to make polarizers and the type of phase plates that might generate these beautiful vortex beams. But we're fortunate, we don't have to do that. We can actually take light, laser light, that's tailored in polarization and phase, and then use that to upconvert and make high harmonic beams that are also tailored in polarization and phase. So for example, if I showed you this movie before for high harmonic generation driven by linearly polarized lasers, you might think that to make a circularly polarized harmonic, one should use a circularly polarized driving laser. But if you do that, you can ionize the atom, but unfortunately, the electron never returns to the ion because the laser just guides it away from the atom, and so it never returns, so it can never recombine to give a circularly polarized X-ray. But what you can do, and this was suggested by theorists, Wilhelm Becker, way back in '95, but nobody noticed the papers, so we rediscovered it and learned how to phase match back in 2015, that if you use a pair of driving lasers with opposite circular polarization, you can in fact both ionize the atom and the electron returns to the parent ion. So you do get circularly polarized harmonics, and you can see that in a photon picture very beautifully, that high harmonic generation has to conserve both energy and photon spin angular momentum. Now, the high harmonic photon can only have 1 unit of photon spin angular momentum. So if you drive with red and blue light, you can only absorb 1 more blue or red photon than you can only absorb 1 more or less blue photon than red photon. And so essentially what you get are beautifully sculpted high harmonics with that now consists of pairs where each pair consists of left and right circular polarization. And so this is sort of a waveform that would be impossible to generate out of any optic. It's really, really beautiful. And more recently, we've been playing with driving high harmonics with OIM or vortex beams, and we've managed to create a light pulse where the orbital angular momentum changes during the pulse itself. So the shape is changing during the pulse from low orbital angular momentum to a high orbital angular momentum. Of course, we know that this will have applications in looking at, let's say, spin dynamics and magnetic systems, but we haven't quite reached applications in this area as yet. So I hope I've given you just a flavor of the type of control we have over short wavelength light. It's really quite amazing. It's quite exquisite, where we can make these broad supercontinua or isolated peaks. We have full temporal coherence and spatial coherence. We can shape the polarization and the phase and really achieve really exquisite control over X-ray light. And it's very fortunate we can do that because X-ray optics, they are difficult to fabricate really well. And so it's great that we can use the ability to control visible lasers and near infrared lasers and use that then to control the X-ray output. So in the next half of the talk, I'd like to tell you about a few applications in looking at different kinds of materials, in particular in imaging and in looking at magnetic materials. But just wanted to reiterate that because we have not had laser-like beams at short wavelengths in the past, many of these spectroscopies, people would use synchrotron free electron lasers when they can get time on those facilities, but much of the work was done with visible lasers. And as you know very well, that if you can make the way, especially if one is looking at nanoscale properties or you need element specificity, if you move to shorter wavelengths and you also have the ability to look at the phase, that gives you just very nice sensitivity to many, many aspects of the material. So we tend to be able to see new things because we have a new light source to shine on our material. And essentially that's what I'm talking about in this particular view graph, that if one has been studying transport or functional properties using visible lasers, very often one is interpreting a scatter pattern, and this becomes difficult at dimensions less than 100 nanometers because you need to use a model to interpret the pattern. And so these techniques tend to work only if you are pretty confident of your materials or your biological science. But if you think about what we're trying to, going forward, we're trying to understand the influence of an interface on coherence. We want to look at buried layers, dopants, materials interdiffusion, coherence, look at spintronic devices. And for all of these, we need sort of better metrologies. And if we want a functional biomicroscope that works without freezing or labeling, then essentially we need a new set of metrologies that can do that, and that can see what is happening. And so I'd like to take 5 minutes in talking about where these light sources are being adopted. I was afraid to put these at the end because I might run out of time. And it's just neat that, for the students in the audience, that if you look at any sort of new area of science or new capabilities, it can take decades to have them adopted for real world application. And the high harmonic community is a very broad community with very strong, many super strong groups in Canada. And it's just so great to see that this technology is beginning to take baby steps to being adopted. So this is work that Henry led at KM Labs and with John Peterson at EMEC. So EMEC is one of the leading industrial R&D for the R&D institutes for the semiconductor industry. So and this became more pressing as EUV lithography became online. There's a long story behind this that Dwayne and Robin and other people in our field know very well. It took a long time, but now eventually Cymer was able to produce a very powerful incoherent EUV source that is being used to print chips and is now being adopted and implemented in real foundries. So associated with that comes the need to be able to look at different materials that might be used for photoresist, for example. So this is a view graph from IMEC, and what it shows, this is a short wavelength laser, excimer laser, that and this is the photoresist pattern that can be produced with an excimer laser versus extreme UV light at 13.5 nanometers. And you can see quite large differences in these two exposures. You can see that the EUV gives you, sharper corners and narrower lines, but you can also see that the line roughness is sort of more, stochastic. And the idea here is that compared to a UV photon that might generate a few photoelectrons when it's absorbed by the photoresist, an EUV photon has 95 eV that will degrade into tens of photoelectrons at the absorption site. And so you get more stochastics in the pattern that's printed. So they'd like to be able to develop better photoresist that might smooth these absorptions better, for example, and generate sharper line edge roughnesses. But the models for the photoresist that they've developed for UV don't work well in the EUV. So they have to go back and really ask, so what happens when an EUV photon strikes a photoresist? What changes can I make chemically to make, to spread that bond breaking more uniformly? And so back a couple of years ago, IMEC decided that they would install one of these harmonic, couple of these harmonic systems to create a real-time functional imaging lab to develop photoresist, but also to look at 2D materials and nanostructured systems and devices. And I like to use this picture because the IMEC lab looks a lot neater than our labs at JILA. So, but it gives you a good feel for the scale of these sources. So this is the femtosecond drive laser. This is just a tight sapphire laser. And then what's shown here are two EUV systems, one that's optimized for 30 nanometers and one for 13 nanometers. And then this looks like a little mini synchrotron beamline, where there's a beamline that comes out here for angular resolved photo emission to look at, and photoelectron microscopy to look at the electronic structure of materials. And then here's for a microscope, CDI, coherent diffraction imaging. I'll talk about that. There's one here for what's called interference lithography and looking at UV masks. And then these UV pump probe to look at these photoresist chemistry. And they've gotten off to a very good start. I mean, these are just amazing teams. They feature this at a lab in the advanced R&D they're doing, and they were recently able to use a very simple Lloyd's double mirror to print very nice 20 nanometer full pitch lines. And so this was done with high harmonic generation. Okay, so in the last section of my talk, I'd like to talk about some applications in imaging. And if there's time, I can talk about using the very, very fast timescales of high harmonics to look at some very fast spin manipulation. But let's hope I'll at least have time to talk about the new types of microscopes. And this coherent microscopy in the X-ray region is really revolutionizing X-ray imaging at synchrotrons, on the tabletop systems that our group works with, and also in the X-ray free electron laser facilities. And the reason why is, we've had X-ray, incoherent X-ray sources for a very long time, well over a century. But if you try to make a microscope based on diffractive optics, which is the kind of lens one has in the X-ray region, these are limited about 10 times the diffraction limited by the fact that it's very hard to make a perfect zone plate X-ray lens. And so the wonderful thing is if one has coherent X-ray sources from synchrotrons, X-FELs, or high harmonic sources, instead of using an image forming lens, one can just simply shine the X-ray beam on the sample, collect the scatter pattern, and then use a phase retrieval algorithm to assign a phase to the scatter pattern, and then do a reconstruction based on then a Fourier transform. And initially, so this was first implemented by our collaborator John Miao at the Brookhaven synchrotron source back in 1999. It was suggested well before then, but by 1999, the coherent flux was sufficient to do a simple demonstration experiment. And for the next decade or so, it was seen as a very sort of exploratory area of science, because a lot of people were very uneasy with the idea of using a phase retrieval algorithm to recover the image. But as the algorithms became more powerful and the coherence of the sources improved, it's now really becoming a mainstream imaging technology. And what I show here are some advances from tabletop systems here on the left and from synchrotron systems here on the right. So we can now make, for the first time, we can get to sub-wavelength resolution imaging at short wavelengths, and these are whole cell cryomicroscopies, and look at the 3D spin texture, for example. But there is a price to be paid, which is the amount of data one has to collect. So what really made these techniques very robust was this idea from John Rodenberg and Pierre Thibault and John Maiden's groups, that if one samples the scatter pattern, a lot of overlap between adjacent spots, there's so much redundant data that the algorithm can very robustly reconstruct an image. And that's become more and more powerful as people have further adapted these techniques. And so one thing our group has done is for looking at, let's say, devices or nanostructures or such, so maybe I should sort of go back here one slide, that usually coherent imaging is implemented in transmission mode in the soft X-ray region, because soft X-rays penetrate structures very nicely, but they don't reflect off structures. High harmonics are very bright in the extreme UV region. And the wonderful thing about that is that in the extreme UV region, materials are very reflective. So what's plotted here is the intensity or the reflectivity from different materials: lithium, silicon dioxide, silicon, silicon nitride, arsenic, carbon, gold, at a wavelength of 30 nanometers as a function of angle. And just like with visible light, if everything is reflective at glancing incidence, that's the same for EUV light. But the other wonderful thing is that there's a contrast. There's a nice contrast. And since coherent imaging gives you the amplitude and phase of your reflected light, there's even a bigger contrast if we extract the phase. And so what that allows us to do is make a microscope where we can put a nanostructure in there, we can build a model. This was the most complicated microscope we've ever built, because what it has to do is we have to scan multiple different angles and then do this tachographic or overlap scanning motion at each angle. And so this, I have to give a lot of credit to an amazing group of students, Michael and Chrissy and Yuka and Nick, who built this and then commissioned it. And then EMAC provided this very nice nanostructure that had a lot of challenges. It had very low reflectivity. It had multiple height samples. It had different regions that were doped differently underneath. But after a couple of years, like 4 years total, if we do design, building, commissioning, and then finally getting all the algorithms right, we were able to make both a spatial resolve map and then a depth resolve map in nanometers into the sample. So the carbon contamination, the silicon nitride nanostructures, the oxide layers, the silicon underneath, and the doping profile. This is in log atomic ratio scale. And the nice thing about this is a relatively large area map. We validated this imaging using the beautiful capabilities of electron imaging and atomic force microscopy. AFM is great. It gives us the height very well, but it doesn't tell you, what is in the material. And of course, EM electron microscopy is great, but the statistics maybe are not good enough to be able to really extract the dopant profiles. So in these maps, these colors designate these same materials underneath the sample. Okay, so how are we looking on time? I could finish now, or I could do one final topic in really using the very fast pulse nature of high harmonics, but I think I'll take my guidance from Dwayne.
Oh, you've got 10 more minutes, no worries.
Okay. So I'd like to then talk about, switching gears from resolving with high spatial resolution, resolving materials. Now I'd like to talk about resolving spin dynamics with very high time resolution. And this is a really interesting topic, because it made me have to, not the first time, have to rethink what we learned as grad students. Personally, was back in the 80s, for how we understood light coupling to metals, for example. So what we all learned back then was that that the heat capacity of the electron bath in a metal is much lower than that of the lattice. So when you shine light on a material, the electrons are excited to very high temperatures, can be well above the melting temperature, but it's fine because the lattice heats up much more slowly due to electron phonon collisions. And the spin system was also thought to heat up quite slowly. So the idea was, our approach was, use the fact that we have this very short burst of light. We can shake up the system and then use the response times to understand how the different spin and lattice and charge systems were talking to each other. And so that was our basic understanding since the short pulse lasers were first used to look at material systems. But it turns out that that's not the whole story. If one is looking at a system with strong interactions, then if the material undergoes a phase change while the electrons are cooling, then you should see that phase change written onto the electron temperature. And actually you can see that. So now we know that this is not a good interpretation for magnetic systems, for charge density wave systems, anything with very strong interactions. And the other very interesting thing we found is that one can actually map new quantum phases, phase transitions, new excited states, and one can really think about a femtosecond laser as a very delicate manipulator of materials, not something that puts everything into a very far out of equilibrium state, but instead very delicately manipulate the electron-phonon and phonon-phonon interactions. So I like this. And in one system where we were able to discover a lot of surprises are in magnetic systems. They've been looked at with femtosecond lasers since shortly after robust high sapphire lasers were available. And this was beautiful work by Geneviève Bigot and Bourpaire, where they excited a magnetic system, nickel, with the femtosecond laser and measured the asymmetry or the magnetic asymmetry, which is the strength of the magnetic moment with the same femtosecond laser. And what they saw is that it took quite a long time for the magnetism to decay. And so because it took such a long time, people speculated that the bottleneck must be how long it takes the angular momentum to dissipate as the sample changes from ferromagnetic to paramagnetic. And so this is the origins from some of these 3 temperature models used in magnetic systems. So essentially, the idea was that the light coupled to the charges quickly, but it took a lot of scattering process to absorb the angular momentum. So it was a cascade of multiple coupled interactions. Now, what was strange about this is that all materials had roughly the same demagnetization curve. And there were theories that seemed reasonable that predicted a very fast spin transport or direct excitations, but nobody ever saw any evidence of this in the material responses. But by using a bunch of different spectroscopies, and those in chemistry know this very well, that every probe measures something different about the materials. And the one very powerful probe is photoemission spectroscopy. So let me just talk about that. Why is that so powerful? It's because if you combine photoelectron spectroscopies with magneto-optic probes, you can actually look at the Fermi edge and fit that Fermi edge and extract the instantaneous electron temperature. You can also look at exchange splitting. And that allowed us to uncover something very unusual, that if you measure the electron temperature as it's being heated by the femtosecond laser pulse, that instead of getting hotter and hotter, as you would expect if there's a constant specific heat, what we found instead that there was a kink in the electron temperature as a function of laser fluence, and that kink had a cusp just at the Curie temperature. So essentially what this yellow region is essentially the heat capacity of the spins. So essentially what we now know is instead of this interpretation of taking a half a picosecond or so to for the angular momentum to be dissipated by the lattice, instead what our measurements show is that there are these super excited states that correspond to high energy spin flips that happen during the laser pulse, where all the energy needed to drive the material through a magnetic phase transition is absorbed. And those high energy magnons then decay to lower energy magnons. And this is what a magneto-optic spectroscopy probes. But by looking at the instantaneous electron temperature, we could see the energy being transferred to these high energy spin flips. And we've seen this in many magnetic materials, that there's almost instantaneous direct transfer of spin polarization by light, either through these high energy spin flips, which we believe may be mediated by exchange scattering, or by just direct transfer of polarization because of the band structure of the material. And so that's what in these Heusler alloys, we've seen measuring the instantaneous magnetism in two different elements in the alloy. We saw that the magnetic moment increased on one side and decreased on another side, essentially because of the band structure. So it's direct light-induced transfer of spin polarization. And so you might ask, so why were these excitations missed in the past? It's because when you look at these materials with visible light, one measures the average magnetism in the alloy or the multilayer, whereas with UV light, because of these different absorption edges, different colors of different harmonics lets us probe and look at what's happening in different sites, for example. So what's shown in black is what one would measure with visible light, which is just that standard demagnetization curve. So with that, I am going to move on to wrap up. Maybe I'll show you one highlight in the last minute of work done at Cosmic, where we worked with Jam Yao's group, Penn State, David Shapiro and others, to now, instead of looking at spin dynamics, we looked at spin texture. So we took a synchrotron beam and focused it onto a nanostructured nickel material. And then through doing a whole lot of data collection, tomography and a vector tomography, where we used magnetic circular dichroism to get contrast. And I'll just finish by using this movie showing this. Oops, I thought I was going to show a movie, and maybe I will have time to show them. Good. Yeah, good. Just showing the beautiful spin texture within this topological constrained metal lattice. And of course, ideally what we'd like to do is to combine the high temporal resolution of soft X-ray high harmonics with these beautiful vector tachotomography techniques to be able to look at the dynamic 3D spin texture in a material. And so with that, I'd like to end by saying, I hope I've given you some flavors of why we say high harmonic sources are a unique quantum technology that allow us to have exquisite control over shortwave and light. We don't know where the limits are, but we're already using high harmonics to discover new materials properties, new properties in magnetic systems, new types of microscopes, and in other work we can look at really, really fast electron-electron interactions. And because everything scales with the wavelength, the measurements can have higher time resolution, higher spatial resolution, and higher sensitivity going forward. And so with that, I really do need to thank a lot of graduate students and collaborators who are responsible for this work. Nathan and Ting and Bin, who did a lot of the structured light, Jun Wenjing and Yin Kao, who did some of those photo emission experiments, and Michael, Yuka, and Nick, who made those beautiful microscopes. There's a lot of alumni too, whose work I talked about, and collaborators from Salamanca and Uppsala, Boulder, Kio, Intel, the LBNL, NIST, of course, John Miao's group at UCLA, and then collaborators from Barcelona. And like to also thank our STROBE team and our funders, and thank you very much for your attention.